All right, so let's get started here. Obviously, I wasn't here at the end of last week for the first lecture on the mole, so we're going to kind of review a little bit about what we should know and then build off that as well. Okay? This concept of the mole is something that's really unique to chemistry because we like to talk about how many atoms that we have in a given chemical reaction, for example. But of course, there's a huge number of atoms that are involved, right? So we use this mole as a sort of convenient way to denote a certain number of atoms. And that number is kind of weird, very specific, all right? 1 mole is equal to 6.0221 times 10 to the 23rd of whatever it is that we're talking about, okay? So we can just sort of use this catch-all term particles to start out with. Okay, so just like if you said you had a dozen eggs, everybody would know you were talking about 12 eggs. If I said I had a mole of atoms, everybody knows I'm talking about this very specific number right here. I'm talking about 6.0221 times 10 to the 23 atoms. And is this a big number or a little number? Times 10 to the 23. It's an absolutely enormous number, right? There is about a mole of water molecules in this bottle right now, right? There's just a huge number of atoms in a container even about this small, right? So we have to use this as the shorthand to talk about this huge number of atoms or molecules, okay? This number is not something that you have to have memorized, all right? If we go to our constants page, we talked about using this portion down here and everything over here. The mole definition is in this box over here, right? So that's 6.0221 times 10 to the 23. You don't have to have it memorized. You probably will just because we're going to use it so freaking often, all right? But we don't have to. It's right here on our constants page. That number, that 6.0221 times 10 to the 23, is what's called Avogadro's number. So you'll hear that term a lot. Avogadro is a dude, like 1800 scientist, super, super old, who helped sort of lay the groundwork for this theory. All right? Okay, so then the other thing here is just terminology-wise. Particles is a catch-all term that we use to describe stuff that's small, right? So we can talk about electrons as particles. You can talk about dust particles. It's just kind of this catch-all term for stuff that's really tiny, okay? So let's just sort of, for vocab's sake, we have particles. And again, that's our catch-all term for small stuff. Okay, but in the world of chemistry, we can be more specific than that. All right, if we're talking about individual elements on the periodic table, we would be talking in terms of atoms. Okay, so for example, 1 mole of chlorine implies that you have 6.0221 times 10 to the 23 chlorine atoms. Okay, and you could say chlorine particles, but it would just sound weird. Okay, because again, particle is this catch-all term for small stuff, but since we're talking about a specific element here, we're talking in terms of chlorine atoms, all right? So atom, strictly speaking, this is the smallest unit for a particular element. Okay, now in chemistry, oftentimes we're not talking about just individual elements, but compounds, right? We're going to take different elements and smush them together to make compounds, right? So NaCl, sodium chloride. We talked a lot about these compounds before in terms of how we name these compounds. Okay, so when we start sticking molecules together, when we start sticking atoms together, we no longer call those atoms. We will call them molecules. These are compounds, but specifically covalent compounds. All right, so for example, I had said that there was about a mole of water in this container right here. Then I would be talking about 6.0221 times 10 to the 23 water molecules, right? Because water is a covalent compound. So I can say 1 mole of water equals 6.0221 times 10 to the 23 H2O molecules. All right, so again, if I have an individual element, we call them atoms. If I'm taking more than one element and I'm putting them together, now we call them compounds. And specifically, if they're covalent compounds, we call them molecules. And this is probably one of the greatest misnomers, one of the most misused terms in all of chemistry. If you have an ionic compound, so for example, sodium chloride, we do not technically call these molecules, and you'll hear people incorrectly refer to them as molecules all the time. But technically speaking, for ionic compounds, 1 mole would be equal to 6.022 times 10 to the 23 NaCl, what we call formula units. Okay, this is the analogy of a molecule, but when you're talking about an ionic compound, we call them formula units. All right, so formula units, these are now ionic compounds. Okay, and why this terminology is important here is because we'll see these different units for our Avogadro's number, right? So whether we're talking about individual atoms, we would use atoms. If we're talking about covalent compounds, we would use molecules. And if we're talking about ionic compounds, we would use formula units. Okay, always that same magic number there, but the context of those atoms, molecules, or formula units depends on what you're talking about. Okay, always that same 6.0221 times 10 to the 23, same Avogadro's number, right? But the back end here will change depending on the context. So just to bring that up so it's not confusing when we switch it up. Cool, okay, so first thing that we should be able to do with this Avogadro's number here is to take this piece of information and build one of those conversion factors, just like we did before, right? We said that 1 inch was equal to 2.54 centimeters, and we stacked them on top of each other to build one of those conversion factors. We're gonna do the same thing with this piece of information here, right? So for example, my 1 mole of chlorine equals 6.0221 times 10 to the 23 chlorine atoms. We have a little conversion factor that we can build here where we're going to stack 1 mole of chlorine over the 6.0221 times 10 to the 23 chlorine atoms. Or, just like we can do before, we can take this and flip it. We can take the 6.0221 times 10 to the 23 Cl atoms on top and the mole of chlorine on the bottom. Right, so just like we did before, we took this equals relationship that we got from our constants page and we built one of these conversion factors out of it. We can do the exact same thing with Avogadro's number here. Okay? And now we would be converting between atoms and this quantity of moles. So what kind of thing could we do with this here? Let's say that I told you that I had 2.5 moles of chlorine, and I wanted to know how many chlorine atoms I had. Well, we're going to take one of these conversion factors that we use, and we're going to use it to cancel out our units just like we did before, right? Same game that we're going to play over and over again in this course is setting up these problems in such a way where we're paying very careful attention to our units, and our units cancel out, leaving us with what we want, right? So now I'm going to start my problem here with my 2.5 moles of chlorine, and I'm going to take one of these two conversion factors here. Which one am I going to pick? The one on the left or the one on the right? right? And why am I going to pick the one on the right? Because that will help me cancel out moles and leave me with what I want, which is atoms of chlorine. So set this up such that moles are on the bottom. Okay, and then I would just punch that into my calculator. Because Avogadro's number is this big number here, you're always going to see represented in scientific notation, right? It would be a huge pain in the butt to represent that in standard notation. So again, we're going to be practicing our scientific notation a bunch in our calculators. Okay, and since it's such a big number, my calculator is going to spit out the answer in scientific notation as well. 1.5055 times 10 to the 24. And what are my units? The chlorine atoms, right? Moles have canceled out. So I'm left with chlorine atoms. And then I'm done. What are we always going to have to do in this course? Sig figs, all right? So we're going to go back and use our rules for sig figs here. Again, this is a multiplication division problem. So I'm going to look, my initial value had 2. Avogadro's number is not an exact number. We're going to always use all the decimal places that our periodic table our constants table gives us, so that we're not limiting with our sig figs as much as possible. But we still do got to pay attention. This number has 5 sig figs. So again, we take all those decimals so that it hopefully doesn't limit us. But we're going to round our final answer here to those 2 sig figs. So 1.5 times 10 to the 24 Cl atoms. Okay, now you will see me be very good about keeping track of who I'm talking about in my problems here. We were talking about chlorine, so I didn't just say moles, I said moles chlorine. Strictly speaking, though, the units are actually just the mole or the atom. It's helpful, and trust me, it'll be very helpful, especially when we start talking about chemical reactions, and there's more than one molecule or compound involved to keep track of who we're talking about. But strictly speaking, the units are not chlorine atoms, but just atoms. So you'll see it in both of those cases. Okay? Again, I'm going to be really good about keeping track of who I'm talking about, but just make note.
So for the homework, it would just be atoms?
Correct. Just the units for the homework. Yep, exactly. Okay, so now I'm going to give you one from scratch here, and you guys are going to do this for me using our Avogadro's number that we took, and we made these little conversion factors out of it here. All right? So now I want to know how many moles contain 4.25 times 10 to the 22 H2O. And since I'm talking about water, what am I going to use? Atoms, molecules, or formula units? Molecules, right? We got a covalent compound here. Okay, so everybody take a second and see if you can't tell me how many moles contain 4.25 times 10 to the 22 water molecules. How many moles of water do I have if I have that many water molecules? right, so now I'm going to take this conversion factor that I built, but I'm going to put water molecules on the bottom so that those units cancel out and I'm left with moles. All right, so now molecules will cancel out, leaving me with moles of water. So I punch that into my calculator, and similar to what we said before, since we're dividing by this number in scientific notation, it's going to be really important that you put it in parentheses in your calculator. Otherwise, you're going to get this absurdly large number at the end of the day. Okay, so punch that into my calculator. I get 0.0705733. And again, we're left with moles of water as our units. And then I'm going to go back and I'm going to do my sig figs. How many sig figs should I report my final answer to? 3, right? So I have 3 in this 4.25. Again, Avogadro's number is not exact, but it does have a good amount of digits. So I'm going to round my answer to 3 sig figs here, or 0.0706 moles of water. Okay, so again, in chemistry, we use this concept of a mole to talk about a specific number of atoms or molecules or particles. Okay, that specific number is 6.0221 times 10 to the 23. So if I say I have a mole of something, you know I have 6.0221 times 10 to the 23 of whatever it is that I'm talking about. All right, and just like before, we can take this equals relationship and we can turn it in to one of these conversion factors that would help us convert from atoms to moles or molecules to moles, depending on the context. Okay? Cool. So, let's go to our periodic table here. All right. We talked a lot about our periodic table when we first introduced it here. Specifically, we have this atomic number up at the top. And this corresponds to how many what are in that element. How many protons are in that element, right? So what makes boron boron is you got an atom with 5 protons. We gave a name and the symbol, right? That's how we refer to it. And then we had this bottom number here, which we called the mass number. And I told you we were going to, or the average atomic mass. I told you we were going to use this quite a lot in this course, but we hadn't really got there yet. Okay? So now's this time. Now we're going to learn how to use this number right here. This 10.811 for boron, for example. This is what we would call the molar mass of that compound. Okay? So that is the mass in grams of 1 mole of that element's atoms, right? So if I had 1 mole of boron, if I had 6.0221 times 10 to the 23 boron atoms, and I put that on the balance, I would see that that came out to a mass of 10.811 grams, right? That's what that number means, is how the mass of exactly 1 mole of that particular element, okay? So we are going to write this in this sort of abbreviated way. So for boron, for example, we said 10.811, okay? So the units here for molar mass are grams per mole. Okay, so we have both the grams and the mole in that unit there. One of these mixed units. Okay, so this is how you'll see this kind of written in this abbreviated fashion here. Importantly though, when we use this in our math, we're going to take this and we're going to turn it into something that looks more like one of our conversion factors. Okay, what we're going to do is stack these units. We're going to separate them out, where we're going to put our 10.811 grams, and I'm going to be good and keep track of who I'm talking about. This is for boron, right? We're going to put one set of units on top of the other set over 1 mole of boron. Okay, so here's this molar mass information, and importantly, this is how we're going to use it in our math. And then we're going to play the exact same game that we've been playing up until this point, where we set it up in such a way that our units cancel out. Okay? All right, so let's grab a different element here. Let's go for oxygen. Whoops, that's not what I want to do. We'll go for oxygen. Okay, I want you to take this piece of information from the periodic table and I want you to turn it into something that we can use in our math, resembling one of those conversion factors. All right. Okay, so I have this 15.9994 grams per mole. But what we're going to do and how we're going to use it into our math is we're going to take those and split them up. So 15.9994 grams of oxygen over 1 mole of oxygen. Okay, now this number is very close to 16. It is not 16. All right, don't be willy-nilly rounding stuff off the periodic table. Some scientists worked very hard to get those 4 decimal places on that molar mass. We're always going to use all of our digits off of our periodic table. All right, we round at the very end when we do our sig fig step. Don't be rounding willy-nilly in the middle. It changes your answer that you will get. All right, so why do we bother splitting this up? Because again, we can use this as one of these conversion factors, right? So what if I wanted to know what is the mass of 2.35 moles of oxygen? Using this molar mass that we took off of the periodic table and then built one of these conversion factors for. See if you can't set this up. Just based on analogy, we haven't done any problem like this, right? But just based on analogy of what we've been talking about with our unit conversions, see if you can't set this up in such a way that'll tell me what the mass of 2.35 moles of oxygen is. All right, so I'm going to start with my 2.35 moles of oxygen. And I'm going to multiply it by this molar mass. And I know that I'm going to multiply it instead of flipping it, instead of dividing it, because I want moles of oxygen to cancel out. All right, so 15.9994 will go on the top. Okay, so then I'll punch this into my calculator, 37.5985. And my units should work out because of the way that I set up my problem where moles will cancel out. So I'm left with grams of oxygen. And then I'm done. Always got to do the sig figs, right? So now we'll go back and apply our sig fig rules. Our moles have 3. Our molar masses are not exact. They tend to have a lot of digits though. That's why we take all of them from the periodic table, so they're not what limits us. All right, so then I would round this to 3 sig figs here. So 37.6 grams of oxygen. All right, so that last number on our periodic table is the molar mass of that compound. It's how much 1 mole of that substance would weigh if you took it and put it on the balance, all right, specifically in grams. And we can use that molar mass as a conversion factor where we split it up. We put grams on top over 1 mole of whatever element it is that we're talking about, okay? And we can use that like a conversion factor. All right, so then maybe more practical than this would be if we went to the balance, we went to the balance and we massed out a certain amount of a substance, and then we wanted to know how many moles of that substance we just went and massed out, right? So now we're gonna go the other way here. Okay, so now I want to know how many moles are in 13.6 grams of sulfur. So I got to go find sulfur on my periodic table, right? That 32.066. This is telling me that there's 32.066 grams of sulfur in 1 mole of sulfur. All right, that's my molar mass information. So then I'm going to start my problem with my 13.6 grams of sulfur. And am I going to multiply or divide by that molar mass? Am I going to keep it as it is or flip it? I got to flip it so that my grams will cancel out, right? So just like with every other conversion factor that we build, we can use it as is, or we can take it and flip it upside down, depending on what units we're trying to cancel out. So in this case, I'm trying to cancel out grams. So that 32.066 grams of sulfur will go on the bottom, and the mole of sulfur on top. So now I'm going to take it into my calculator, punch the 13.6, and divide it by that 32.066. So 0.4242125, and now I'm in moles of sulfur, or my units, right? Grams have canceled out. And then go back and do sig figs. So 0.424 moles of sulfur. Boom. All right, so you just went to the balance and you massed out 13.6 grams of sulfur. How many moles did you actually have? That's what we would use our molar mass for. All right, so now let's see if we can combine this with what we learned about Avogadro's number as well. Okay, so now I'm going to ask, instead of asking how many moles are in 13.6 grams of sulfur, I'm going to ask, hold up, how many sulfur atoms are in 13.6 grams of sulfur? Okay, so I have my mass of sulfur here, the 13.6 grams. So I can use my molar mass, just like we did before, 13.6 grams of sulfur. If we divide by our 32.066 grams of sulfur in 1 mole of sulfur, our molar mass, this would put us in moles. But now the problem is not asking me to stop in moles. It wants to know how many sulfur atoms I have, right? So if you see one of those words, atoms, molecules, particles, that's going to be a dead giveaway signal in your brain that you need to be using Avogadro's number. That's the only way we have to work with that particular unit, okay? So just by seeing sulfur atoms here, I know that I'm also going to need, in addition to my molar mass, that Avogadro's number, 6.0221 times 10 to the 23. In this case, it would be sulfur atoms in 1 mole of sulfur. All right, so we can talk in terms of how many moles of sulfur we have, or we can make one more jump using Avogadro's number to talk in terms of specific sulfur atoms. All right, so now I would just take my Avogadro's number, paying close attention to my units. I'm going to put moles on the bottom, which means that that's 6.0221 times 10 to the 23 goes on top, right? Sulfur atoms. Okay, so then if I punch that into my calculator, I get 2.55412 times 10 to the 23 sulfur atoms. And being good about sig figs, I would again be restricted to my 3 sig figs. So my final answer would be the 2.55 times 10 to the 23 sulfur atoms. Now, truthfully, in chemistry, we don't usually talk in terms of number of atoms because there's such a big, cumbersome number. It's kind of a pain in the butt. We like talking in terms of moles, okay? But again, that's because we always know what a mole is. The definition of a mole being 6.0221 times 10 to the 23 of whatever it is that we're talking about. Okay, so up until this point, we've been working with individual elements, right? Individual atoms. But again, a big focus in chemistry is not just the individual elements, but the compounds that they make when we start putting them together. So what if I wanted to know how many grams were in 3.6 moles of water? All right, we've been using these molar masses to jump between grams and moles, right? And so when we're talking about particular elements, all we got to do is go to the periodic table and grab that number for that particular element. But now we're talking about the molar mass of compounds. All right, that's what I'm going to need in order to answer my problem here and jump from moles of water into grams of water. I need to know the molar mass of water. Okay? So the molar mass of H2O, what we're going to abbreviate as capital M, H2O, molar mass. All right, these aren't too bad. All we're going to do is we're going to go and grab that information from our periodic table for each of these elements, right? So the molar mass of water is going to be the molar mass of hydrogen times 2, because in my formula for water I have 2 hydrogens, plus the molar mass of oxygen. All right, so we're just going to sum up all of the elements that appear in our compound, making sure to multiply by whatever subscripts we see that appear in that formula. All right, so my periodic table here, I'm going to look for hydrogen, the smallest element, 1.00794. And now I'm going to add the molar mass of oxygen, that 15.9994. Okay, so summing all that together will give us the molar mass of our compound. And to be clear, make sure everybody can see why I'm multiplying the molar mass of hydrogen by 2. Right? Why am I multiplying the molar mass of hydrogen by 2, but not the molar mass of oxygen? Because if I look at my formula here for H2O, I have 2 hydrogens but only 1 oxygen, right? So make sure that you account for the number of that particular element that you have. Now, this is an addition problem here. And remember, for addition and subtraction, we have different rules for sig figs. But I'm going to make y'all a deal here. As long as you always grab every digit off of the periodic table, we can ignore our sig fig rules and just use what the calculator spits out. All right? That way we're not having to do too much of a pain in the butt for sig figs here. So I'm just going to always use the full number from my periodic table. And then I can just use whatever my calculator spits out. So 18.01528. And again, we're going to use all those digits. And what are my units on this 18 point whatever? Grams per mole. Absolutely. The molar mass. Always both of them together. Not just grams, not just moles, but grams per mole. So now that we have this molar mass, see if you can't finish off this problem here and tell me what the mass of 3.6 moles of water is. All right, and so again, the trick, if we got this part down, the rest of it isn't too bad. Now we just have to pay attention to our units. The trick here is making sure that we can take that molar mass and learn how to turn it into something that we can actually use in our math, where we split up those units, putting grams on top and 1 mole on the bottom. All right, so that's how we're going to use that molar mass in our math. So now going back up, we're going to take our 3.6 moles of H2O, and I'm going to be multiplying by that molar mass because I want moles of water on the bottom. Okay. This would be 64.85500. And my units? Grams. My moles cancel out, so I'm left with grams of H2O. And then sig figs were 2. All right, my 3.6 has 2 sig figs, so I'm going to round this off to be 65 grams of water. All right. So if we're talking about an individual element, we just grab that number off the periodic table. If we're talking about a compound, we have to calculate its molar mass by summing up the molar mass of all those individual elements. Okay? So let's go back to our periodic table here. We're going to do another one. All right, and so how can I make this a pain in the butt here? All right, let's say how many grams are in 14 moles of magnesium chloride. so what makes this tricky is now we got to roll in what we learned how to do in the last unit here, which is to take this name of magnesium chloride and turn it into the formula for magnesium chloride. I have to know how many magnesiums and how many chlorines there are in magnesium chloride before I can calculate the molar mass. Okay, so we got to do this the long way here. We're going to look at our periodic table and we're going to ask ourselves, what's the charge of a magnesium ion and the charge of a chloride ion? Right? Based on our periodic table, here's magnesium. What's the charge of the magnesium ion? +2. And what about the chloride ion? -1, right? Because of where chlorine lives. So when I put these together, magnesium chloride is MgCl2, right? So when I go to my periodic table, I'm going to have to take the molar mass of magnesium and then add 2 times the molar mass of chlorine. All right, so don't forget this step here that we learned how to do in our first unit, which is to construct the formula of these compounds from the name itself, right? I'm going to make you guys practice that all throughout the semester here, so make sure we got that down. Okay, so now we have our molar mass of magnesium, or we have our compound formula rather. I'm going to take the molar mass of magnesium and twice the molar mass of chlorine. That's how I'm going to get my molar mass of my compound. All right, and again, I can ignore sig figs as long as we always take all of the digits off of our periodic table here. So I'm going to take the 24.3050 plus 2 times the 35.4527, and I get 95.2104. Again, molar masses are not just grams or moles, but grams per mole, right? Grams over moles. So then if I start with my 14 moles of MgCl2, I'm going to multiply by that molar mass so that moles stay on the bottom. All right, I punch this into my calculator. I get 1332.94. How many sig figs should my final answer have? 2. I want everybody to take a second and report our answer here with the proper units and to the proper number of sig figs. Let's make sure that we can do that for these big numbers here. All right, so I'm going to be rounding to this hundredths place here. Remember, I'm not going to chop off those digits. This is not going to round to 13. This is a very different number. If I told you I was going to give you this much money rounded to 2 sig figs and I gave you $13, you'd feel a little gypped, right? Remember, we can't change the number. We have to leave it as 1,300 grams of MgCl2. Kind of smush it in there. All right, so from the periodic table, we have this last number here that we hadn't really worked with yet. These are the molar masses of this compound. They tell us the mass of 1 mole of whatever that element is. We can use those molar masses as conversion factors to help us jump from grams to moles or moles to grams, depending on which direction we're trying to go. And then if we have a compound, so for example, magnesium chloride, we're going to use that formula and figure out in order to calculate its molar mass. So I would grab the molar mass of magnesium and 2 times the molar mass of chlorine in order to get my compound's molar mass. Cool. All right, we'll pick up with all this next time.